The sidewalk crack forest, the ecosystem growing between concrete. At first glance, a sidewalk crack seems like damage, a thin fracture in concrete, a light where weather, weight, and time have broken the smooth surface of the city. Most people step over it without thought. Some see it as neglect, a flaw waiting to be repaired, but for seeds, moisture, fungi, ants, and roots, that crack is not damage at all. It is an opening, a narrow forest corridor carved into stone. What makes sidewalk cracks extraordinary is their disproportionate ecological value. A gap only a few millimeters wide can support an entire miniature ecosystem. It gathers dust, traps moisture, catches seeds, concentrates nutrients, and creates shade along its edges. Over time, what begins as a slight fracture becomes one of the most biologically active strips in the urban environment. The story starts with accumulation. Wind pushes dry leaves across the pavement until they snap in the crack, passing through green just into the opening. Rainwater carries pollen, soot, and tiny soil particles into the narrow space. Bird feathers, insect wings, fur, and microscopic fragments of organic matter scatter there day after day. The city is constantly shedding material, and the crack acts like a trap, collecting the smallest pieces of life. The first organisms to truly colonize are often microbial. Fungospores land in the damp sediment after rain. Bacteria multiply in the thin organic layer formed by dust and decomposing leaf fragments. Algae may coat the shaded inner walls if moisture lingers. The invisible layer becomes the human foundation of the crack forest, turning bare concrete edges into living soil. Then come the seeds. A grass seed blown from a roadside verge, a dandelion perch drifting between buildings, parsley and herb seeds dropped from a balcony above. Even tiny tree seeds from nearby street canopies. Each one only needs a few stable conditions, a little substrate, repeated moisture, and a place where roots can push downward. The crack offers its own tree. The first green shoot is often fragile, but it changes everything. A single sprout shades the cracked floor, reducing evaporation. Its roots anchor sediment, preventing rain from washing nutrients away. Fine root hairs create pathways for water retention. As the plant grows, dead leaves from the same seedling fall back into the crack, feeding decomposition and enriching the substrate further. The opening slowly transforms from a line into a linear soil ecosystem. Roots are the engineers of their hidden forest. As they thicken, They push against the concrete edges, widening the fracture by fractions of a millimeter. Each rainfall expands and softens the surrounding material. Each dry spell contracts it again. This cycle creates more space for roots, insects, and microbes. Over months or years, the plant is not just surviving in the crack, it's actively building the habitat larger. Moisture is the crack, the most important currency. Rainwater naturally follows the slight depression in pavement, concentrating runoff along fractures. Even morning dew they can linger longer in the shaded lights than on exposed concrete. This repeated wetness creates a micro-riparian zone, a miniature riverbank ecosystem where moss, liverworts, and tiny ferns may establish if shade conditions allow. Insects quickly discover the benefits. Ants use sidewalk cracks as highways, protected from urban foot traffic. And direct sun, beetles hide beneath the tiny leaf litter trapped in the stem. Springtails feed on mold in the damp soil. Aphids may colonize the fruit shoots, attracting ladybugs and lacewings. Spiders uncoil silk thread between plates that emerge from neighboring fractures. The crack becomes a corridor of movements, stretching block after block. Temperature gradients make the habitat even richer. The top edge of the crack may hit rapidly in direct sunlight, favoring drought-tolerant moths and heat-loving ants. Just a centimeter deeper, moisture remains cooler and more stable, supporting fungi and root microbes that creates vertical habitat layering in one of the tiniest ecosystems imaginable. Human movement shapes the forest too. Sows desolate seeds, crush leaves into mold, and transport microbes from one plot to another. Bicycle tires splash nutrient-rich powders into steams. Street cleaning may remove surface debris, but often leaves the deeper organic core effect intact. Even bats walking the same route contribute fur, skin cells, and nutrient stasis. The most fascinating part of the crack forest is persistence through disturbance. It exists in one of the harshest environments possible. Compacted surfaces, intense heat, heavy foot traffic, pollution, and frequent drying. That because the crack creates protection and constraints resources, life continues to return. One cracked plate leads to more lead to trapped moisture. Fungi feed roots widen the crack. The crack supports more life. There is ecological success in miniature. From above, it may look like a wet breaking through stone, but from inside the system, it is a forest edge, a riverbank, a root zone, and an insect considered corridor compressed into a hidden into a line no wider than a finger. The sidewalk crack teaches one of the deepest lessons that open energy. Life doesn't wait for ideal conditions. It begins wherever space appears, and that tiny green light is only the beginning. In part 2, we will go, deep, go deeper into the root zone beneath the behavior, where fungi, ants, water channels, and microbial life turn the crack into an underground forest floor hidden below the city. What we see above the sidewalk is only the smallest visible expression of the crack forest. The real ecosystem lies below the concrete surface, in the narrow dark node where roots, fungi, moisture, and tiny animals turn fractures for pavement in an underground forest floor. Beneath airy green soot rising through stone is a hidden architecture of line extending downward into the city's water spaces. The crack itself is only the entrance. Below it, the space widens irregularly. Concrete slabs rarely sit perfectly flush against the ground. Tiny voids from beneath turn from shifting oil, erosion, and repeated cycles of heat and rain. These voids become subterranean chambers where food, fire sediments, and moisture lingers, and roots can spread far beyond the visible seam. The predominant force here is the root system. What begins at a single grass blade above might already have a dense network of fungi roots extending sideways beneath the pavement. The roots do more than anchor the plant. They stabilize loose sediment forward to downward and create microscopic tunnels through the substrate. Each road leaves behind organic compounds that feed surrounding bacteria and fungi, turning the crack into biologically active underground zone. That zone, the hydrosphere beneath the sidewalk, is also the bit itself. Fungi tracks between root fibers, forming micellar bridge that transport moisture from and nutrients across tiny pockets of soil. In shaded sidewalks near trees, the fungal grabs may even connect cracked plants to larger roots from nearby trees, allowing the miniature forest to tap into the underground nutrient network. Moisture behaves differently below the pavement. On the surface, water evaporates quickly under sun and road traffic. But beneath the slab, evaporation slows dramatically. Rain that shifts into the crack can remain just for days, moving sideways through dust, sand, and decomposed organic matter. They create a cool moisture reservoir, a hidden wet within the damp, dark microbial life flourishes. Bacteria break down crust leaves that roots, pollen, and dust washed into the crack. Fungi decompose total fibers from stem and bark fragments, actinomized, though the microbes responsible for the smell of earth after rain. Many colonize the deeper substrate, especially in outer cracks where organic matter has accumulated for years. Sand of rain or pavement often partly comes from the invisible communication working below the stone. Ants are among the most important animal energy engineers of the underground floor. Sidewalk cracks provide perfect protected entrances to nesting systems. Ant colonies excavate tiny chambers beneath the slabs, bringing finer particles upward while carrying seeds, insect remains, and organic debris downward. That tunnels improve aeration and water movement, making the crack ecosystem even more habitable for roots and microbes. They create a remarkable partnership. Roots stabilize the crack, fungi feed the roots, ants improve soil structure, microbes recycle organic matter, moisture remains trapped below the widened crack, supports more plants, the underground becomes self-reinforcing. Beetles and springtails exploit the little rift zones beneath the slab edges. Tiny worms move through the moist substrate, feeding on decomposed material. Mice patrol fungi grows in shaded neighborhoods. Bugs may use their voice at daytime shelters, emerging at night to feed or leaf fragments caught near the surface. The thermal stability of the underground crack floor is one of its greatest ecological strengths. While the concrete above may become scorching in direct sun, the void beneath remains cooler and more stable. In winter, the slab also shows sudden temperature drops, allowing microbial and root activity to continue longer than exposed soil. That buffering effect makes crack ecosystems surprisingly resilient year-round. Nearby street trees often expand their system dramatically. Their larger roots may intersect with sidewalk fractures, creating shared underground corridors. Fine roots from west and moss in the crack can occupy the moisture-rich zones around the tree roots, effectively forming a microforest understory beneath the pavement. Human disturbance adds new layers. rather than simply destroying the habitat. Vibrations from footsteps and bicycles shake dust deeper into the voice, rain splashed nutrients from cups, and street soil into the cracks. Construction dust, pollen, bad fur, and urban soot satur into the underground chambers. The city continually feeds the forest floor without realizing it. During drought, the hidden layer becomes a refuge, while visible shoots above may wilt, roots and fungi remain alive below, waiting for the next rainfall pulse. The cracked forest survives not through constant surface growth, but through subsurface persistence. After storms, the underground floor briefly behaves like a sponge forest. Water fills the chambers, rehydrating microorganisms and flushing dissolved nutrients along root channels. Ants adjust nest depth, gums rise closer to the surface, fungal growth accelerates through softened organic layers. The next burst of green above the pavement is powered entirely by what happened unseen below. This is what makes the sidewalk crack forest such a profound ecosystem story. The visible width is only the canopy, the true forest is beneath the slab. The pavement we think of as solid is actually full of hidden life zones, root corridors, ant chambers, fungal moss, moisture pockets, seed pines, microbe little beds. The city is not as huge as it appears. Every fracture becomes an underground refuge where life gathers, wastes, and slowly pushes upward again. In part 3, we'll return to the surface and follow how insects, moths, weeds, birds, and rain transform the cracks into a street-level migration corridor stretching across the block. When we return to the surface, the sidewalk crack is no longer just a fracture or a root zone seen at the scale of an entire street. It becomes something larger, a linear migration corridor stretching across the block, connecting plants, insects, fungi, moisture, and even birds through one of the narrowest habitats in the city. A single crack rarely exists alone. Concrete sidewalks are full of seams, expansion joints, curved edges, broken tiles, and straight fractures that intersect like branches in a river delta. What seems like isolated damage is actually a connected network of ecological pathways. Seeds move through it, ants travel along it, rain follows it, moss expands from one downlight to another. The entire sidewalk begins to behave like a forest trail system written into stone. The first and most constant travelers are ants. For ants, the crack is a protected highway. It shields them from direct sun, reduced exposure to predators, and provides navigation lines defined by sand trails. Colonies made you once seem as a foraging route to tree pits, another as a connection to building walls, and a third as a statue dropped foot near benches or cafe edges. Across a whole block, the routes overlap into a complex surface transport network. Beetles and spiders use the corridor differently. Ground beetles patrol the dam edges after sunset, hunting springtails and soft-bodied insects among the leaves. Little trapped insects, small jumping spiders, use grass shoots emerging from cracks, lookout towers, and pushing flies that land on the green place. Upwebs may span between neighboring webs rooted in separate cracks, turning the corridor into an aerial hunting zone. Rain activates the migration corridor in dramatic ways. Water naturally seeks the lowest parts in pavement, and cracks become miniature stream channels guiding runoff across the block. During storms, pollen, dust, seeds, dead insects, and organic fragments are scraped along the narrow lines. The crack transforms into a seasonal river system at sea level, redistributing nutrients from tree pits, gardens, balconies, and street debris into new habitats. The movement of seeds is especially powerful. A dandelion seed caught in one crack may be flushed 2 meters down the block into a wider seam. Grass seeds from a nearby lawn may collect where the pavement dips. Most spores spread through repeated splash. Over time, vegetation appears in clusters not by chance, but by the hydrological logic of the crack network. Birds interact with the corridor more often than people realize. Sparrows and pigeons forage along seam-rigged sidewalks because the cracks trap softened seeds, insect larvae, and moisture after rain. A bird hopping from seam to seam is effectively moving through a feeding corridor built by pavement, stretch, and weathering. At dawn, the corridor is especially alive. Dew clings longer in the cracks than on open concrete, drawing springtails and ants toward the moist edges. Tiny flies gather near mossy patches. Robins and wagtails may inspect the seams for insects. The sidewalk, which appears lifeless in midday heat, rapidly becomes a moving ecosystem of foraging roots and moisture lies. Moss and live ghosts create the corridor's green understory. In shaded streets or older neighborhoods, dam seams may develop continuous green strips that visually resemble miniature forest floors. The moss ribbons stabilize dust, trap additional moisture, and create cooler surfaces for microbes and tiny invertebrates. They also make the crack more attractive to insects that prefer humidity, strengthening the corridor further. Human movement paradoxically helps certain the migration network. Zoo transport seeds and fungi spores from parks, gardens, and even indoor plants. Bicycle tires splash nutrient-rich water deeper into the seam. Street sweepers redistribute fine dust that later settles into the cracked edges. The corridor is constantly being researched and rewired by urban motion. Seasonality changes the species using it. In spring, cracks become germination highways, full of seedlings and insect traffic. In summer, drought-tolerant grasses dominate exposed seams, while shaded cracks preserve moss and fungi life. In autumn, falling leaves create mold ribbons along the corridor, feeding decomposers. In winter, frost expands fractures, opening new routes for roots and future water flow. Each season redraws the migration map. The corridor also extends vertically. Cracks near walls connect to climbing vines, mossy bricks, drain pipes, and even balcony runoff zones above. Rainwater carrying nutrients from flower pots may drip directly into pavement seams below, linking upper building ecosystems to street-level crack forest. What begins as a line on the sidewalk becomes a multi-level urban life route. One of the most beautiful truths here is that the crack corridor creates continuity in fragmented cities. Parks may be blocks apart, trees may stand isolated, and concrete walls that the cracks between slabs quietly connect them through seed flow, insect roots, and moisture transport. That is the sidewalk's hidden forest part. Not a part for humans, but for roots searching water, ants carrying food, spores seeking shade, beetles hunting prey, and seeds waiting for the next rainfall ponds to carry them farther down the block. The city's biodiversity often survives through the narrow continuities. Without cracks, the pavement would be far more sterile. In part 4, with them, the block becomes stitched together by life. In part 4, we'll close the story by revealing how the crack forests act as resilient zones for the entire neighborhood, influencing street trees, pollinators, birds, and the long-term ecological health of the city itself. By the time we reach the final layer of this story, the sidewalk crack is no longer a flaw in concrete. It has become something much larger, a resilient layer woven through the city's hardest surfaces, quietly having urban life survive heat, drought, fragmentation, and ecological isolation. What makes the crack forest so important is not its beauty, though a green seam through stone can be unexpectedly beautiful. Its true value lies in what it does for the wider neighborhood. Its roots stabilize loose sediment beneath the pavement. Its leaves shade the same, lowering surface temperature. Its stems slow water runoff, allowing moisture to seep downward. Its flowers feed pollinators. Its seeds expand biodiversity into new structures. In cities, it is one of the hardest forces shaping life. Pavement absorbs sunlight and releases it slowly, creating urban heat islands that can make streets far hotter than surrounding rural areas. Correct vegetation interrupts that process. Even a narrow strip of moss or grass reduces direct solar exposure on the concrete edges, slightly lowering temperature in the seam and the immediate air above it. Multiplied across thousands of cracks in a neighborhood, and the effect becomes meaningful. The crack forest forms a distributed cooling mesh, a fine-grained network softening the city's thermal extremes. That cooling matters for insects, ants, beetles, spiders, and springtails. You shaded seams at daytime refuges when exposed concrete becomes too hot. Pollinators moving through streets can put out flowering weeds rooted in cracks. Even earthworms beneath the pavement benefit from cooler moisture zones created by root shade and slowed evaporation. The crack forest also strengthens storm resilience. During heavy rain, soaked concrete sheds water rapidly, increasing runoff and flooding pressure. Cracks interrupt the flow, roots open pathways for infiltration, while organic matter trapped in seams acts like sponge material. Water slows sinks and disperses underground instead of racing directly into drains. Across a full street, thousands of tiny seams collectively behave like a hidden absorption network, reducing flash runoff and feeding moisture back into the soil beneath sidewalks and nearby tree pits. Street trees are among the biggest beneficiaries. The roots of large urban trees often struggle against compacted, dry soil. Crack ecosystems provide additional infiltration points where stormwater and nutrients can reach. Deeper layers, fine roots from trees may extend toward the stems, exploring the moisture-rich corridors created by grasses, moss, and decomposed litter. The sidewalk crack becomes part of the feeding system of the street canopy above. It creates a beautiful ecological look. Trees drop leaves become mold in cracks, cracks feed microbes and roots improve infiltration. Moisture supports tree growth. Trees shade the sidewalk. Shaded cracks preserve life longer. The city's visible canopy depends partly on its invisible fractal network, but also benefit from the resilient layer. Sparrows, pigeons, and wagtails forage in cracks for seeds and insects. During dry periods, the timber preserved in shade seams maybe one of the few remaining insect-rigged zones on a hop block. What seems like random bird picking is often precise ecological use of the crack forest. Over the years, the green seems to influence how neighborhoods evolve biologically. More flowering weeds mean more pollinators. More pollinators support balcony plants, community gardens, and street trees. More insects support birds and spiders. More roots mean more soil stability around pavement edges. The crack forest becomes a foundation layer of succession as important grows even greater under climate change. As cities face hotter summer, stronger storms, and longer dry spells, small resilient habitats become critical. Sidewalk cracks provide exactly the kind of microfield many organisms need. Cooler than exposed pavement, wetter than open surfaces, safer than traffic lanes, richer than polyconcrete, connected across long distances. They're tiny, but they are continued, and continuity is what resilience depends on. The most powerful feature of this ecosystem is philosophical as much as biological. The places we consider broken are often the places where life repairs itself. The crack is that where nature re-enters the built world. It's where roots test the limits of stone, where moss rise green across gray, where ants build beneath human footsteps, where water finds memory in pavement lace. A city without cracks may look perfect, but ecologically it is less forgiving, less predictable, and less alive. A city with cracked forests is porous, adaptive, recoverable. The sidewalk becomes a living emergency layer, ready to absorb water, shelter insects, feed birds, and restart plant succession after every disturbance. That's why the cracked forest belongs perfectly in the hidden ecosystems of everyday life series. Hidden everyday places series. It reveals that resilience don't always live in parks or forests. Sometimes it survives in the thinnest green light between two slabs of concrete. The next time you walk down a city block, look at the seams beneath your feet. That grass play is not just a weed. That moss ribbon is not deliberate. The ant light is not random. It is the city quietly keeping itself alive.